Welcome to our AP Precalculus lesson on exponential functions. By the end of this video, you will be able to identify and describe the key characteristics of exponential functions, including their general form, domain, range, end behavior, and key properties. Understanding these functions is fundamental because they model a wide variety of real-world phenomena, from population growth and compound interest to radioactive decay. Let's begin. Our first objective is to define an exponential function. What does it look like in its purest form? The general form of an exponential function is f of x equals a times b to the x, where a is the initial value and b is the base or growth factor. There are a few crucial conditions for this form. The initial value a cannot be 0, because if it were, we'd have f of x equals 0 for all x, which is a constant function, not an exponential one. So our first condition is a cannot equal 0. Next, the base b must be positive, and it cannot be 1. This means b must be greater than 0 and not equal to 1. Why? If b were negative, the function would jump back and forth between positive and negative values, like minus 2 to the power of 2 is 4, but minus 2 to the power of 3 is minus 8, which isn't the smooth growth or decay we expect. If b were 1, then 1 to any power is just 1, which again would make f of x equal to the constant a. These conditions ensure the function behaves as a true exponential. Let's explore the roles of a and b. First, a is what we call the initial value. A is the initial value. It represents the y-value of the function when x equals 0. Let's prove that. If we substitute 0 for x, what do we get? F of 0 equals a times b to the 0. Since any non-zero number raised to the power of 0 is 1, we have f of 0 equals a times 1, which is just a, so a is always the y-intercept of the graph. Now let's turn our attention to b, the base. The value of b dictates whether we have exponential growth or exponential decay. For simplicity, let's assume a is positive for now. If the base b is greater than 1, the function exhibits exponential growth. If b is greater than 1, we have growth. This means that as the input x increases, the output f of x also increases. The graph will rise from left to right. For example, consider f of x equals 2 to the x. The initial value a is 1, and the base b is 2, which is greater than 1. This is a classic growth function. The outputs grow larger very rapidly. Let's look at the outputs. F of 1 is 2, f of 2 is 4, f of 3 is 8. For each unit increase in x, the output doubles. Conversely, if the base b is a fraction between 0 and 1, the function displays exponential decay. If b is between 0 and 1, we have decay. In this case, as x increases, the output f of x decreases. The graph will fall from left to right. A great example is f of x equals 1/2 to the x. Here a is 1, and b is 1/2, which is less than 1. This function is decaying. Let's examine the outputs. F of 1 is 1/2, f of 2 is 1/4, f of 3 is 1/8. With each unit increase in x, the output is halved, representing decay. Exponential functions have several unique properties that set them apart from other functions. First, their domain is all real numbers. Domain, all real numbers, or negative infinity to infinity. There are no values of x that you cannot plug into b to the x. The exponent can be any real number, a positive, a negative, a fraction, or 0. Second, their output values have a special relationship. The output values are proportional over equal length input intervals. This is a key distinction from linear functions. Output values are proportional over equal length input intervals. For a linear function, we have a constant difference over equal intervals. That is, we add the same number. For an exponential function, we have a constant ratio. We multiply by the same number, the base b. Third, the function is always increasing if b is greater than 1, or always decreasing if b is between 0 and 1. This means the graph never changes direction. Exponential functions are always monotonic. They are either always increasing or always decreasing. Fourth, if a is positive, the graph is always concave up. This is a property we explore more in calculus, but visually it means the graph always curves upwards, like a bowl. Due to being always increasing or always decreasing and always concave up, these functions have no relative extrema or points of inflection. Because the graphs don't change direction or curvature, They have no points of inflection or relative extrema. One of the most important features of an exponential function is its end behavior. We need to understand what happens to the function's value as x gets very large in the positive or negative direction. As with our previous properties, the behavior depends heavily on the base b. Let's first consider the case where b is greater than 1. As x approaches positive infinity, our growth function also approaches positive infinity. We write this as x approaches infinity, f of x approaches infinity. Think of 2 to the x. As x gets bigger and bigger, 2 to the x grows without bound. But what happens as x approaches negative infinity? As x approaches negative infinity, f of x approaches 0. Let's see why. 2 to the minus 1 is 1/2, 2 to the minus 2 is 1/4, 2 to the minus 3 is 1/8. As x becomes a larger negative number, the output gets closer and closer to 0. Now let's look at the decay case, where b is between 0 and 1. As x approaches positive infinity, the value of a decay function approaches 0. As x approaches infinity, f of x approaches 0. Think of 1/2 to the x. As x gets large, the fraction gets smaller and approaches 0. And finally, what happens as x approaches negative infinity for decay? As x approaches negative infinity, f of x approaches positive infinity. Let's use our example. 1/2 to the minus 1 is 2, 1/2 to the minus 2 is 4, 1/2 to the minus 3 is 8. As x becomes more negative, the output grows infinitely large. The end behavior we just discussed leads directly to the concept of a horizontal asymptote. A horizontal asymptote is a horizontal line that the graph of a function approaches as x approaches positive or negative infinity. For the standard exponential function, f of x equals a times b to the x, with a not equal to 0, the horizontal asymptote is the line y equals 0. This means the function's output values get closer and closer to 0, but never actually reach it. This is a key characteristic to remember when sketching these graphs. It's important to note that this asymptote can be shifted vertically. For a function like g of x equals a times b to the x, plus k, the horizontal asymptote would be at y equals k. The constant k shifts the entire graph up or down. Let's quickly review the key distinctions between exponential functions and their more familiar cousin, linear functions. The fundamental difference lies in their rate of change. As we discussed, a linear function has a constant rate of change. This means, for equal length input intervals, the output values change by a constant amount. This creates a constant difference. Constant difference leads to linear functions. A car traveling at a constant speed, say 60 miles per hour, is a linear model. After 1 hour, it's 60 miles away. After 2 hours, 120 miles. After 3 hours, 180 miles. Each hour, the distance increases by 60 miles. An exponential function, on the other hand, has a constant ratio. For equal length input intervals, the output values are multiplied by the same amount. Constant ratio leads to exponential functions. A population of bacteria that doubles every hour is an exponential model. If you start with 100 bacteria, after 1 hour you have 200. After 2 hours you have 400. After 3 hours you have 800. The change is not constant. It's proportional to the current amount. A classic AP Precalculus point to understand is that exponential growth eventually outpaces linear growth. No matter how large a constant difference you start with, a constant ratio will eventually become greater. Let's put our knowledge to the test with an example. Suppose we have the function f of x equals 3 times 1/2 to the x. The function is f of x equals 3 times 1/2 to the x. First, let's identify the key characteristics. What is the initial value, a? The initial value, a, is 3. This means the y-intercept is at the point 0, 3. Next, what is the base, b? The base, b, is 1/2. Is this a growth or decay function? Since 1/2 is between 0 and 1, it's a decay function. Because b is less than 1, we have exponential decay. The graph will be decreasing. What is the domain? The domain is all real numbers, negative infinity to infinity. What about the horizontal asymptote and end behavior? For decay functions with positive a, as x goes to infinity, f of x goes to 0, and as x goes to negative infinity, f of x goes to positive infinity. The horizontal asymptote is y equals 0. The function approaches 0 on the right and infinity on the left. So, we've successfully identified all the key features from the equation. Let's summarize what we've learned today about exponential functions. We started with the general form, f of x equals a times b to the x, where a is the initial value at x equals 0, and b is the base. The base b determines growth or decay. A base greater than 1 means growth, while a base between 0 and 1 means decay. Key properties include a domain of all real numbers, constant ratios over equal intervals, and a graph that is always concave up. And finally, we saw that standard exponential functions have a horizontal asymptote at y equals 0, with their end behavior depending on whether it's growth or decay. By identifying these key characteristics, you can now understand and analyze any exponential function. Great job, and I'll see you next time.